state of the stresses are, we can tell exactly what is the normal stress and the shear stress on that fracture. I'm going to give you one tip now, so you remember the motivation of this example is that when you have a ratio of shear stress to normal stress which is high, that would mean that that fracture will be more likely to reactivate in shear and will be more likely also to have a high permeability. So it has a direct application on what we're going to see. And usually we do this by using the Mohr circle and locating where actual fractures are within this Mohr circle is going to tell us whether those fractures are more likely to be reactivated in shear or not. We'll get back to that. And now, let's continue by trying to understand the Mohr circle and to decompose the Mohr circle in two parts. All right, so I'm going to do it in 2 dimensions, but the example graphically it's kind of difficult to do in 3 dimensions, but we're going to do it numerically. But the concept is exactly the same. But for now, let's go with a 2D Mohr circle. So let's say that I have a Mohr circle like this one, and where I have the principal stress sigma 1 and the principal stress sigma 2. The Mohr circle, there are 2 things that you have to notice. First is how far from the origin the center is. That tells you the average compression in that particular point. The further to the right, the more compression you're going to have. And the second thing to notice here is the radius. The radius of the circle tells you how much shear you have in that particular point as well. And it's very convenient many times that we divide this state of stress in order to make it simple for analysis into 2 components. One component, which is going to be the isotropic component, and it's just going to be a point here, which is going to be the average of the 2 other stresses, and the other component is the shear. What do you think the 2 values at the x-axis is going to be for a Mohr circle that I have to draw right here, so that this one plus this one is equal to that? R. R, and how much is R? R from where? From the center. And how much is R?
Sigma 1
Sigma 1 minus sigma 2 divided by 2, and this is negative sigma 1 minus sigma 2 divided by 2. And that's a Mohr circle that corresponds to that state of shear. So decomposing the Mohr circle or the state of stress in 2 is going to give me one component, which is isotropic. Here, the Mohr circle is just so small, it's just 1 point. And this component is what is called the deviatoric component, and it is just pure shear. And this is going to be very useful to us because we're going to use this division quite a bit. From here, I want you to notice too that a Mohr circle, sometimes we just can simplify it with two numbers. Where is the center and where is the radius? And now we're going to convert it into a more meaningful terms, but we're going to do it in 3 dimensions. So let's do this same thing, but now with the stress tensor. All right, so let me find the corner of the page here. This is going to be this stress tensor. And we're going to do exactly the same thing that we did before, but we'll do it as matrix operation. So we have to divide it into an isotropic and a deviatoric component. Okay, the isotropic component, we're going to call it sigma m, and the m is from mean. And since this is an isotropic component, what is the value of these elements here and there? 0. And here is the isotropic component, and sigma m is going to be equal to sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3 divided by 3. I didn't show this yet, but I'm going to make a point about this later to convince you that it is true. Notice that those are just the elements from the diagram. And the second part is going to be the deviatoric component. And now I do include the shear terms. Which may be different than 0. And in diagonal, I have to subtract the mean stress. This is exactly the same thing that we did before. And this component is going to be called the deviatoric component of the stress tensor. If I want to summarize this operation in instead of writing the entire matrix just as one variable, this operation is the stress tensor is equal to a scalar quantity, which is sigma m, times the identity matrix plus the deviatoric stress tensor, which in this case I'm going to call it S D. Well, remember this is the identity matrix 3 by 3. So it gives you the same thing that you see over here. Okay, so we can do this, and we can use this mean stress because we have some properties in tensors that are very useful for us to deal with tensor quantities. And those are called the invariants of a stress tensor. And guess why they are called invariants? Because they don't vary above, and especially because they don't vary with respect to the coordinate system. So you can write this stress tensor in any coordinate system, and the value is going to be exactly the same. So the first invariant of the stress tensor is just the summation of the diagonal terms. It doesn't matter in which coordinate system you have it, it's going to be always the same. And if it is always the same, if I were to write this stress tensor in the with the principal stresses, what would be the value of the first invariant? What would be the diagonal elements in a matrix which is the matrix of principal stresses? It's going to be sigma 1, sigma 2, and sigma 3. So this is going to be also to the summation of the principal stresses. And by extension from this equation, we see that the mean stress is equal to the first invariant divided by 3, which is that equation over there. And again, the good thing about this is that you don't have to convert this stress tensor into principal stresses in order to calculate the mean stress. Always the summation of the diagonal elements has to be the same. If it's not the same, something is wrong, okay? It always is the same. This is the first invariant, and this one is similar to the value of C, how far the Mohr circle is from the center, and it gives you the model compression for a particular point. The second invariant is a little bit more complex than the first one. I don't want you to memorize this equation. The first one, yes, I want you to memorize that, okay? It's easy. The second one, it's a little bit more complicated, and again, you don't have to know this by heart, but you have to know that it exists and it's important. The second invariant quantifies the importance of the diagonal elements, because now in the equation we have diagonal elements, and we have diagonal elements in here and off diagonal here terms in here. So the second invariant quantifies the importance of the off diagonal elements. So it will be more or less equivalent to the radius of the Mohr circle in 2 dimensions, but not exactly the same, because we have to do one more step in order to get there. But for now, let's just leave it like that. And there's going to be a third invariant, which is equal to the determinant of this matrix. And that other invariant also quantifies how different the values are with off diagonal and diagonal, but it's a little bit more difficult to visualize as the other ones. Okay, we're going to call I from invariant to the invariance of the stress tensor. And there are going to be 3 other invariants, which we're going to call by J. J1 of the Deviatoric stress tensor, which is this one. So this stress tensor is the Deviatoric part, and it has its own invariants, J1, J2, and J3. Let me ask you, what is going to be the first invariant of the deviatoric stress tensor of this one?
I don't know.
Sigma 1, 2.
No.
0.
0. Why 0? Yeah.
Because sigma 1, 1, sigma 2, 2, sigma 3, 3.
Yes.
Basically just sigma magnitude over 3 and then you subtract it.
Exactly. J1 is going to be 0. And this 0 is similar to the Mohr circle. Now we're just dealing with this. I'm asking you basically what is the center of this Mohr circle? It's at the center, it's 0. And what is the J2 of the deviatoric stress tensor? Well, you can use this equation that we had in here, or you can use another simpler equation that, again, I'm not going to ask you to remember by heart, but it is written like this. And this one tells you also a quantity similar to the radius of the Mohr circle. And you see this quantifying the difference between sigma 1, sigma 2, and sigma 3. If all of those were the same, J2 will be 0. But if they are not the same, this is not going to be equal to 0. This parameter I2, it also quantifies some of the shear amount, but also mixes the diagonal elements. So it's not directly the radius. If you want to get the radius of the equivalent of the radius in a 3D Mohr circle, you have to calculate the second invariant of the deviatoric stress tensor. And that will give you directly the amount of shear in 3 dimensions as just one single number. So, long story short, the only thing that